Question is about vanadium ions. Table 3 shows some standard electrode potential values. Use the data in Table 3 to explain why Zn, so Zn is here, it's a reducing agent, it's on the right, reduces aqueous solutions of VO2 1+ to V2+, but is not able to get them to go from V2+ to V. So it's using the electrode potentials. Now, there's a whole series here, and we can see that the electrode potential of this first equation here is greater than our zinc equation, as is this next equation, as is this next one. So we could actually write a whole series of inequalities, but the important equations to look at are the last one that can happen and the one that can't happen. And for a reaction to happen, the electrode potential of the reduction, so the reduction of V2 3+ to V2+, this is what's happening here, left-hand side, right-hand side, is greater than the standard electrode potential of zinc 2+ to zinc, which means that V3+ can be reduced by Zn. So the thing on the right is the reducing agent. So Zn can reduce V3+ to V2+. But then if we have a look here, the E0, the standard electrode potential of Zn2+, in fact, let's do it the way around for the vanadium. Vanadium 2+ vanadium is less than. So if it's less than, it can't do this reaction. Zn cannot, because it's less than, cannot reduce V2+ to V. Identify the species in Table 3 that can reduce VO2+ all the way to vanadium. So it needs to be less than, and it needs to be on the right-hand side. Reducing agents are always on the right-hand side. This inequality would have to have a greater than symbol, and the only one that would work for would be magnesium. Two half cells. So we've got the Fe2 plus Fe, which if we look down the table is the one with a minus 0.44 electrode potential. And then this equation here, it's the third one down, is a plus 0.34 electrode potential. Calculate the EMF of the cell. So it's the more positive one minus the more negative one. How far apart are they on the number line? So that is 0.78 volts. Give the standard cell representation. So you put the more positive one on the right-hand side and the more negative one on the left-hand side. Remembering that the higher oxidation state species is closer to the salt bridge, and the thing furthest away from the salt bridge needs to be the thing that you can attach the electrode to. So if you think about your two equations, the negative one is going backwards, Fe is going to Fe2+, which is what our standard conventional representation now shows. Our other equation, if you remember it from the other page, was like this. So the higher oxidation state species is this one, because this is +4 and this is only +3. Not the charge, it's the oxidation state. So we've got VO2+ in acid. They're in the same state symbol. They're both AQ. And then it's turning to V3+, still AQ. You can't connect a crocodile clip to those solutions. You need an electrode, so we use platinum, and platinum's a solid, so it has a solid line between it. Half equation at the negative electrode, I actually already wrote at the top. The negative electrode is the left-hand side where oxidation occurs. So if you go to the table, you take the equation and you reverse the direction. 0.151 grams of impure NH4VO3 is added to dilute sulfuric acid to form a solution containing VO2 plus ions. All the VO3 1- ions are converted to VO2 plus. The VO2 plus are then reduced to V2 plus by reaction with zinc. The excess zinc is filtered and washed. The filtrate containing the V2 plus ions is titrated with manganate, and we've been given a concentration and a volume and an equation, and the equation is 3 manganates to 5 V2 pluses. Calculate the percentage purity, so we're going to need to find the mass to express it as a percentage of the 0.151 grams. So let's find the number of moles of manganate from the volume and the concentration. So 29.43 centimetres cubed. Let's put that into decimeters cubed and times by 0.02, because that was our concentration. And we're getting 5.886 times 10 to the minus 4 moles. Now, using the ratio, 3 manganates need 5 vanadiums, so the number of V2 pluses would be 5 over 3. We need to go from 3 to 5. So on your calculator, you can work that out. 9.81 times 10 to the minus 4. Now, it shows you that the V2 plus came from the VO2 plus, and that is in a 2:2 ratio or 1:1. And it says that all the VO3 plus are converted to VO2 plus, and that's 1:1. So this is also the number of moles of VO3 1-, because they all came from that place, which is the number of moles of ammonium vanadate as well, because there's 1 VO3- in an ammonium vanadate. So if we want to find the mass, we're going to do mass is Mr. moles, MR times moles. So we'll add up the MR of ammonium vanadate and times it by our moles. And that's coming out to be 0.115 grams. And then we want to express that as a percentage of the 0.151 grams that were in the question. And that is coming out as 75.9%. Give your answer to 3 significant figures. Now, I've kept all my numbers on the calculator. If you do some 3 significant figure rounding, you may get 76.0%.